Yay!
Yay! Hi everyone. I'm going to take a little sidebar in this video. Generally, I'm going to try not to lecture. Usually, I want to solve problems, and I kind of am. I'm going to say I'm solving a problem in this one. It's not one that you'll typically see in a book, but it's just really important, and it's not often pointed out in books. So this is sort of a maybe marketing-wise, I can call it a bonus episode, right? But here's the idea. What we have is a mass that's going to slide down a plane. This is a very typical example. You'll see lots of problems like this. And the way we typically solve the problem, here's what people tell you to do. The way we usually solve the problem is, okay, we usually have a coordinate system. Oops, let me go back. Usually we have a coordinate system that's like X and Y. Looks like that, right? X to the right, Y is up. But what you'll be told is to solve this problem, what you should do is you should like twist your coordinate system so that the X runs down the plane and then the Y is normal to the plane like that. And that's right. That's what you should do. But there's really rarely a good explanation given as to why you should do it that way. What happens if you don't? Right? So what I'm going to do is go through this example, which is actually pretty simple if you do it the right way. And it's actually kind of hard if you do it the wrong way. I just want to show you what happens if you try to do it normally. And that'll show you sort of the power of this technique of changing coordinate systems. Okay, I got a mass sliding down the plane. So what's happening? I got my M. So I know I have my mg is directed straight down. I'll put the arrow there in just a second. And then I have a normal force, right? Normal to the plane. And it's normal, right? Sometimes we get spoiled in thinking the normal force is always straight up. It's not. It's always normal to the surface. That's the only thing the surface can do is push back normal. The surface can't push to the side. That would be really weird. So the normal force is pointed like up like that. So this is going to be my N. This is going to be my mg, right that way. Let me go through and show you all the things that are the angle theta, because we're going to need all these little things that are theta. For example, theta is the amount that the plane is inclined. That's theta, up there, that angle. It turns out. If you're not used to drawing these things, you might wonder, well, why is it that angle? You can kind of make a movie in your head. If you imagine the plane, if you imagine theta going down to 0 and the plane becoming more horizontal, that N will start pointing more and more vertically, right? It's that angle that goes away, just like the theta goes away. So if I'm ever in doubt, what I do is I sort of make a movie of it in my head. I imagine theta going to 0, and then I imagine what other angles would go to 0. Well, that one's going to go to 0. So that's my little theta up here. And we're also going to need this angle. We're going to need to make a triangle out of that. We're going to need the amount of gravity that's acting down the plane, which is going that way, and then the amount of gravity that's acting normal to the plane, which is that way. And if I make that little triangle, that's going to be useful. You might wonder why we need that. That's going to be useful for us once we change our coordinate systems. If we make that little triangle where this is the right angle back here, then as theta goes to 0, it's this angle that disappears, right? So there's our little angle theta also. All right, so let's go through and use this coordinate system. Let's use just the ordinate, like if you had no idea how to do this problem and you would just say, okay, X is going to the right, like always, Y is going up. So let's see, there's no friction yet on this plane. Let's do frictionless. Let's keep it easy. So what you do is the usual thing. You do the sum of the forces in the X direction is equal to the mass times how it accelerates in the X direction. Okay. So what forces are acting in the X direction? Well, I got a little bit of that N is going in the X direction, right? It's tilted to the right a little bit. And that's a vertical angle theta. So you got to be a little bit careful. The thing that we want is the x component. We want that. We want the x component of that normal force. That's opposite to the angle, right? So that gets a sine, not a cosine. So this is going to be n sine theta. Another way to think about it is that sine is the function. If theta goes to 0, sine is the thing that goes to 0, right? And if theta goes to 0, the x component of that normal force goes away. So that makes sense. All right, so there's a little bit of n going to the right. So I got n sine theta. And that's it. That's all that's happening. So this is equal to max. Cool. And by the way, this is going to be equal to ma. Now a is going down the plane, right? So this is going to be ma cosine theta, because here's my horizontal. That's my angle theta. That's the same angle. It starts to get kind of confusing now. So, okay, there we go. Ma cosine theta. Now I do it in the y direction. In the y direction, what do I have? I have the component, the other component of n. That must be n cosine theta, the adjacent side. And then I got minus mg, right? And that's all that's going on there. So this has to equal, oh, let's be careful. It's may, that's ma sine theta. But look, we're going down the plane, and down the plane is a little bit negative in the y direction, right? So I have to be a little bit careful, and I have to say minus ma sine theta. That's may. We're going down a little bit, so that y component is negative. Okay, what we're after is a. Remember, in almost all these problems, we want to know a. A is what? We want to know the acceleration down the plane. Because remember from kinematics, if we can solve for the acceleration, we know a lot about this thing. We know how fast it's going to be moving at some time. We know the position after some time. So usually what we're going to be after in a lot of these examples is a. We want to know the acceleration. All right, so I got to solve for that a. There's an a over there. All right, what do I do? Well, it's a tricky algebraic thing. Let's try this. How about this? Let's solve for n. Let's get rid of n. Let's get rid of that thing. So n is going to be ma cosine theta over sine theta, right? So this is going to be, the y equation then is going to be ma, look, we're going to get a cosine squared, ma cosine, and this is going to be over sine theta. And then I'm going to have a minus, here's my minus mg equals minus ma sine theta. Oh, that's going to be nice. Watch this. So what I can do now, let's swap those two terms. I'm going to bring ma sine theta to the left and then mg over to the right. So I can get rid of, I hate minus signs. Let's get rid of the minus signs. So ma cosine squared theta over sine theta plus ma sine theta equals mg. Oh, it's past time. Let's get rid of those m's. There's an m in every term. It turns out it doesn't matter what the mass is. That's kind of interesting. That'll be a theme as we go along. So m goes away. Let's multiply through it by sine, because this will give us something neat. So a cosine squared theta plus a sine squared theta equals g sine theta. Ooh, now look at this. Look at this. I can factor out the a, and then I have a times cosine squared plus sine squared. Well, you know that, right? That should be ringing some bells. That's 1. So it's just a. So what we get out of all this is just a is g sine theta. Very cool. But look, that was a little bit of algebra, right? We had two equations, two unknowns. N and a were unknown, so I had to get rid. I even got kind of mixed up at the beginning. I forgot what I was supposed to do. So then it hit me, oh yeah, I got to get rid of the n first, and then I can solve for a. So it was kind of a substitution. I had to remember, trig identity and so on. So get the right answer. That is certainly the right answer. So if theta is 30 degrees, for example, if theta is 30 degrees, remember the magic sine of 30 is a half. So this means that a is 5 meters per second squared, half of the acceleration of gravity. Neat. So we get the right answer. It's just that, I mean, maybe there's an easier way. That was just a lot of algebra. So is there an easier way to do it? And the answer is yes. So what you do is you twist your coordinate system, right? Let's try this. The reason is because your choice of coordinate system is arbitrary. You can solve this in any coordinate system you want. You can invent any new one you want. And because these are vector equations, vectors are the same quantities in every coordinate system. They may have different components, but the vector is always going to have the same length, right? An angle in any coordinate system. So let's twist our coordinate system. And the rule is, how do you know how to twist it? The rule is make x be in the direction that the thing is accelerating. In other words, make x down the plane. It's going to accelerate down the plane. So let's make x our direction of acceleration. Okay, so with our new scheme, let's do it over here. What does this imply? In this new direction, the sum of the forces in our new x direction is, well, now see, n just purely goes in the y, right? Our y is normal to the plane. So I don't have to worry about n. The only thing that's going in the x direction is that component of mg that's headed down the plane. What component? That's this. Let me make it a different color. I'm able to do color. Make it green. This. Right? It's that component that I want. That's the component of gravity down the plane. Well, it's opposite to the angle, right? So if it's opposite to the angle, it gets the sine. That's the thing that disappears if theta becomes 0. So this is mg sine theta. And you know what? From now on, that's just going to be something that, since we've done it once, then we're good. So from now on, I'm just going to say gravity acting down the plane is just going to be mg sine theta. That's just what it is. You might as well just use it. So that's the only force down the plane in our x direction. So this must be equal to ma. And look, a doesn't have components here, right? Because the entire a, that's the whole idea, is that a, all of a is going in the x direction. So we're just sort of done with that equation. And then I can write down the y equation if I want. In the y, I've got all of n is going in our y direction. So n minus, and then I've got, maybe it's a different color. I've got this. There's the component of n that's perpendicular to the plane. So that's the adjacent side to the angle. So that must be mg cosine theta equals 0. It's not accelerating in that direction, right? We want it to stay on the plane. It's not accelerating on or off the plane. So I can make that equal to 0. So this tells me that the normal force is mg cosine theta, which is an interesting thing. We will come back to that. We'll be using that as we go. That's kind of cool. All right, let's talk about it just for a second because it's neat. Mg cosine theta. Okay. Is this the right thing? What happens if theta is 0? If theta is 0, then there is no inclination of the plane. It's horizontal. And what is cosine of 0? It's 1. So n is just mg. Well, that's what you're used to, right? That's just a mass sitting on a table. N is just equal to mg. Neat. What happens if cosine is 90? If cosine is 90, if the theta gets big, well then, if the angle is really, really big, like this, and there's like a box or something, the normal force is the contact force between the box and the surface. Well, it's almost like a sheer cliff, right? As the angle gets close to 90, as this angle gets close to 90, that thing almost has no contact anymore, right? And you reach the limit when theta is 90, cosine of 90 is 0. And at that point, there is no contact. The normal force is 0 because there is nothing keeping the box contacting the plane, because in that case, it's a vertical sheer cliff. So anyway, that's kind of neat. So the normal force is not always equal to mg. Sometimes when you do a lot of problems at first on horizontal surfaces, you sort of get locked into n equals mg. It's not. If there's an inclined plane, it could be a little bit less than that, just governed by that cosine. Okay, anyway, all of that was just, I wanted to bring it up, but it turns out it doesn't make any difference because look, this has nothing to do with the acceleration, right? N mg cosine theta. There's no a in there. We didn't even have to write that one down. So that doesn't even matter. We can just go back up here, cross out the m's. Look, that's it. We got the answer with no work. Almost no work. We just wrote it down. It was just the equation in the x direction. There was no trig substitutions. There was no two equations and two unknowns, right? That trick of, if we're looking for A, make A be in one direction, that gets us a long way. That's a really useful trick. So aligning our coordinate system with the acceleration, twisting our coordinate system like that, is going to be a tool we're going to use over and over again, because, I mean, you'll get the right answer if you do your algebra right, no matter what you do. It doesn't make any difference. You can twist your coordinate system however you want, but this is the easy way to do it. Look, we just wrote down the right answer, right? Sometimes problems are such that if you choose your coordinate system in the right way, the answer just sort of magically floats up to the surface with no work. So we got our A equals G sine theta two different ways. And again, this is a fairly simple problem, but I just wanted to show you, because we're going to be using this twisted coordinate system trick a lot, and I just wanted to take a minute to show you, or a few minutes, I just wanted to show you what happens if you don't, right? That's what, like teenagers, you tell them, twist your coordinate system, and teenagers are all like, what happened? What if I don't? What are you going to do about it? Maybe I don't want to twist my coordinate system. And you're all like, all right, fine, don't then. But the algebra is going to be kind of overbearing, and there's a lot of room for error in there. So after a while, you'll understand why it is that the wise and old masters are right. We twist our coordinate systems to make the problem really, really easy.